This video explains how porous silicon is formed and why photoluminescence of porous silicon occurs. First, I introduce silicon and porous silicon, then show the behavior of porous silicon under illumination, followed by the electrochemical oxidation of silicon, the mechanism of electrochemical dissolution and pore formation, and finally, the photoluminescence mechanism of porous silicon. Silicon makes up 28.20% of the Earth's crust by mass, making it the second most abundant element after oxygen. The picture on the right shows a silicon wafer with a thickness of less than 1 mm and a shiny, mirror-like surface. This bulk silicon does not exhibit photoluminescence in the visible light spectrum due to its small bandgap energy. Porous silicon, formed from bulk silicon through electrochemical reactions, is a nanostructured material with numerous nano-sized pores. The picture on the right shows a porous silicon layer fabricated from the silicon chip on the left. The picture on the left, taken with a scanning electron microscope, shows the surface of a P+ type porous silicon layer with numerous nano-sized pores. The SEM image on the right illustrates a cross-sectional view of the porous silicon layer shown in the left, with pore sizes of approximately 30 nanometers and a thickness of approximately 1 micrometer. Porous silicon is characterized by its ability to exhibit photoluminescence. Unlike bulk silicon, when exposed to light with a short wavelength, for example 365 nanometers, porous silicon emits light with a center wavelength of around 680 nanometers. Next, I will explain how this porous silicon is formed. Porous silicon is formed by etching bulk crystalline silicon in an aqueous electrolyte containing hydrofluoric acid. The schematic above illustrates a two-electrode cell designed for porous silicon production, where the silicon electrode acts as the anode and the platinum electrode serves as the cathode. When a constant current is applied to the silicon/HF/platinum system via a DC power supply, electrochemical reactions occur simultaneously at both anode and cathode. To drive the electrochemical corrosion of silicon, a positive current is applied to the silicon electrode, while electrons are consumed at the platinum cathode. The primary electrochemical reaction at the platinum electrode is the reduction of protons to hydrogen gas, resulting in the formation of bubbles that rise from the cathode. At lower applied currents, oxidation at the silicon electrode predominates, following a two-step process, an electrochemical step and a subsequent chemical step. This reaction produces hydrogen gas and silicon hexafluoride ions. The hydrogen gas escapes into the air, while the silicon hexafluoride ions dissolves in the solution, creating pores on the silicon surface. This process is the key reaction responsible for porous silicon formation. In pore formation experiments, several parameters influence the process, including the electrolyte composition, dopant type, and concentration. For example, P+, P++, N+, N+, N++, applied current, temperature, and light intensity. Moreover, multiple competing mechanisms can simultaneously affect pore growth. Next, I will explain the important mechanisms contributing to the electrochemical pore growth process in silicon from a microscopic perspective. Pore formation proceeds in the vertical direction rather than the transverse direction. There are some mechanisms for this formation. Due to the high radius of curvature at the pore tip, an enhanced electric field is generated at the bottom. This intensified field attracts more valence band holes compared to other surfaces, accelerating the electrochemical reactions at the pore tip. Consequently, pore growth is predominantly directed downward along this enhanced field. As the filament becomes thinner, the resistance to the movement of the hole increases, and it does not advance to the top of the filament but moves toward the solution. Between the filament surface and the liquid surface, a depletion layer develops, and the hole is depleted. As a result, no reaction occurs on the surface, and it does not move sideways. Through these mechanisms, pores are formed mainly in the vertical direction. And, once pores are formed, their form does not change. Porous silicon is a nanocrystalline structure of bulk silicon, which means that the particle size is smaller than in the bulk silicon. This causes a quantum confinement effect, which increases the band gap. The increased band gap makes porous silicon emit light, whereas bulk silicon does not. This is photoluminescence. Photoluminescence is the emission of light when electrons in the valence band are excited by absorbing light energy, move into the conduction band, and then release light energy as they return to their normal state. This photo shows PL intensity wavelength obtained when irradiated with a laser beam of 405 nanometers wavelength. The actual porous silicon has nanostructures of various sizes, resulting the Gaussian distribution of the PL spectrum. The FWHM of the PL of this sample is approximately 190 nanometers,